Hello and welcome again to my Physics Online video lecture supplement series. In today's video, I wanted to actually make a supplement for the Physics with Calculus class, and basically I wanted to work through an additional example for this class. Then it basically goes with lecture 7, which is the Energy and Conservation of Energy lecture, and specifically it goes with part 2 of this set of lectures, which is the part on two types of potential energy, which sort of has the alternative title, what happens when the force that provides the potential energy is not constant. And so this example is as follows. How much work is done by gravity upon an object which slides from point A down to point B along a circular path? And just for simplicity, we just want to know what the force, what the work done by gravity is as this object slides from A to B. There is a very simple solution to this question. I'm choosing this more to illustrate an approach to problem solving than because this is a particularly hard question. First, I'll show you the easy solution, and then we'll do the slightly more involved solution as a double check. So the simple solution to this one is to say that work is always F dot delta R, or I'm going to actually use a delta L for this problem, so sort of change of what I'm using to represent the same thing. This will become clear later. Basically, though, you'll notice that no matter where on the circle our object actually is located, the force of gravity is always pointed straight downward, like so. And so F for gravity is negative mg j hat. So, here's the center of our circle. J hat is in the y direction, and I hat is in the x direction. So force of gravity is always negative mg j hat, and that means that when it's dotted with delta L, no matter what delta L happens to be, as it turns out, it's always tangent to the circle. So here delta L is like this, here delta L is more like this, and then here delta L is more like this. You notice that this angle is changing, but if you take j hat and dot it with all these things, what you end up with is only the j hat component of delta L. And so this is basically going to be mg times L sub y, if you will, which is just another fancy way of saying delta y. So work should be mg delta y, which is mgr, since this right here, this starting point, is actually level with the center of the circle, and our end point down here is at the bottom of the circle. So delta y is equal to r. So that's our simple solution to it. And you can see this because each time that you take the force in the delta L part, delta L can be broken into delta x and delta y. And so delta L is basically delta x times I hat plus delta y times j hat. And since we're dotting this with the j hat, this component goes away because I hat dot j hat is 0. And so you basically are just adding a bunch of little delta y's together. And when you add a bunch of little delta y's together, you just get the total change in height. So that's basically the reasoning behind the simple solution. Now, though, I want to look at a slightly more complex way of doing this, because this other way might be more helpful if we were to ask for, say, a force that is neither in I hat or in j hat direction, but is actually changing. For example, if we had a tangential force or something. But I'm going to do this for gravity still because we know what the solution for gravity is. So this lets us verify that this method actually will work. Okay. In general, we can write that the work done by whatever force is going to be the integral of this differential work. All right, so the differential work is going to be force dotted with the differential displacement vector, dl. And so this just is true by definition. So this right here is basically integral f dot dl. And so what we have to do here is figure out what this dot product is going to yield. The limits of integration are also important, but they're sort of given in the problem. We have phi is running from pi to 3 pi over 2, and I'll show you what that is in just a sec. Basically, the idea is that if I start at A and I end at B, and I move along this whole path length here, then this whole path length might have a length given by L, and L should be, since we're using phi to represent the angle around, should be the radius of the circle times delta phi. We learned about that in the rotational motion segment. So this basically is another way of saying f dot, we'll call it r d phi, times, for lack of a better vector symbol, I'm just going to write phi hat, because if you look at what dl is doing at any given point on this circle, we'll take this point for example, f is straight down, dl is like this. If you take this point right here, again, f is straight down, dl is tangent to the circle, and in fact, dl just kind of always points in this tangent to the circle way, which I'm going to define as the phi hat direction. So recall that if you have two vectors, A and B, and you dot the two together, that your resultant is A times B times the cosine of whatever angle is between A and B. So, for example, if this is the A vector and this is the B vector, then this angle right here is theta. So what we need to do at this point is this dot product right here basically becomes f times r times d phi times the cosine of some angle between f and r. So therefore our integral, given again that the force is the mass times free fall acceleration, our integral basically at this point looks like work is integral, limits are from pi to 3 pi over 2, and then what's inside the integral basically is going to be like a m times g times r times cosine of theta d phi. And so we want to basically define this term in terms of the differentials. We want theta in terms of phi in order to evaluate this integral. So to do that, one way of basically doing that would be to just draw phi and dl at random points around this circle. So if our work is given by this integral from pi to 3 pi over 2 mg r cosine theta d phi, then we could draw, recalling of course that this whole part right here is basically from that dl term. We could draw what fg looks like, and we could draw what dl looks like as a function of this angle phi. So here, this would be the force, and this would be the DL. And so this is at phi equals 0, and what we have is theta equals 180 degrees. So theta, you notice, is from the difference from these two, and they're in opposite directions, so you get 180 degrees. Now we'll go up to say phi equals 45 degrees. And again, the force has to be this way. Now the displacement dl is like this. And it's worth actually defining which direction we're going to go in for our dl. And so by convention, I'm just going to go the counterclockwise direction. So this right here will be theta. So theta is here. Theta would be the same on either side here. It's not the same either side here. So how do we get this angle theta? Okay, first of all, let's go ahead and put that phi is 45 degrees here. Turns out that theta in this case is going to be 135 degrees. So how do we get that? Well, this radius right here has to be perpendicular to dl. That's by definition true of dl being a tangential motion, and the radius is always perpendicular to the tangent line. And so basically, if I draw a little dotted line over here, then it's also perpendicular with this dotted line. This dotted line is sort of the negative of dl. All right, and if I draw F coming down all the way to here, well, F has to be perpendicular to this, because this right here is the 0 degree radius, which is in the I hat direction. F is in the negative j hat direction. So I have phi here. I have this perpendicular F and call it baseline. So that means that this right here has to be whatever 90 minus phi is. So this right here is also 45 degrees. And since this plus this is 90, that means that this right here is also 45 degrees. Okay, well, this angle between theta and F is therefore 90 plus 90 minus 45, or if you want, it's 90 plus 45. Either way, you get a theta equals 135 degrees. Okay, so now let's pick the next one. That would be the one where F is straight down like this, and where dl is straight over like this. So there's dl, there's F, and this is perpendicular, but this also happens to be angle theta. So at phi equals 90 degrees, I get theta equals also 90 degrees. Okay. And I can basically just keep doing this around the circle as I go. Over here, we end up with, here's dl, here's F, we end up with phi is 135 degrees, theta is 45 degrees. Here at point A, we have that F and dl are in the same direction. So here we have that phi is 180 degrees and theta is 0 degrees. Down here, we end up with dl in this direction and F in this direction. We have to be consistent. We still have to do this counterclockwise direction to get from dl to F. So this whole angle, if you look at it, is actually going to end up being a fairly substantial angle, right? It is 315 degrees, in fact. So this is basically theta equals 315 degrees. But recall that 315 degrees is, by the way, as phi is at 225 degrees. Recall that 315 degrees, if we were just going around the circle, would put us over here. And that's the same thing as going 45 degrees in the clockwise direction. So this is also equal to negative 45 degrees. So I'm going to put that negative 45 degrees in there for a reason. We'll come back to it in a sec. At the bottom of the circle, we have F here. We have DL here. So this is phi equals 270 degrees, and this is theta is equal to also 270 degrees. But that 270 degrees can also be written as minus 90 degrees. In other words, we've got 90 degrees this way. Last but not least, we'll put in one here. F is here. Whoops. DL is here. And then here's our angle. So we have phi equals 315 degrees. Theta, in this case, is going to be equal to negative 135 degrees, or positive 225 degrees. Okay, now the reason why I put these negatives in here is because if you go around the circle, a pattern emerges. Theta in this case is equal to what with respect to phi? Well, if you take 180 degrees and you subtract phi, you end up getting theta every time. So 180 degrees minus 0 is 180. 180 degrees minus 45 is 135. 180 minus 90 is 90. 180 minus 135 is 45. 180 minus 180 is 0. 180 minus 215 is negative 45, hence this 315 degree angle, and so on. So the pattern that we've established here is that theta is equal to 180 degrees minus phi. Okay, so that means that this integral that we got to do for work really has something like this. So let's pull all the constants out. So we have mgr integral from pi to 3 pi over 2 of the cosine of theta, but cosine of theta is the same as saying cosine of 180 degrees minus phi times d phi. So now we might want to try using a little bit of trig identity. You know that cosine of x minus y is equal to cosine of x cosine of y plus sine of x sine of y. Whoops. So if we have 180 degrees minus phi, that means that we can say, so here's 180 degrees minus phi. That's cosine of 180 degrees times cosine of phi plus sine of 180 degrees sine of phi. And of course, this right here is equal to 0. This right here is equal to negative 1. So this term right here is basically therefore saying that cosine of 180 degrees minus phi can also be the same as just negative cosine of phi. So now that means that our integral looks something like this. Work is mgr integral from pi to 3 pi over 2 times basically a negative cosine of phi d phi. So basically that means that the work is going to be, if you integrate cosine of something, you get the sine of that thing. So we basically have mgr sine phi, limits of integration from pi to 3 pi over 2. And so you evaluate this guy, sine of pi is 0, sine of 3 pi over 2 is negative 1. I probably added an extra minus sign or dropped a minus sign when taking a dot product, but we have basically come up with that the solution is that gravity does a work of mgr, which is the solution that we got with the simple method above. So now you have a method for finding the work done by not so much a varying force as a force that's applied over a displacement whose direction is varying with respect to the force. So I hope that you find this video helpful. Thanks for watching though.